January 2008. The Boeing 777 is the gold standard for commercial aviation. For more than 10 years, the plane has logged 2 million flights without a single major accident.
Clear to land.
But less than 1,000 feet above London's Heathrow Airport, all that changed.
Pete, I can't get power on the engines.
What do you mean?
It's not giving me power.
This can't be happening. I thought if I don't do anything, then everybody will die.
Mayday! Mayday! Speedbird! Speedbird!
Whatever brought down one of the world's most technologically advanced airplanes can't be found at the crash site.
And they had the pilots, they had the passengers, they had the aircraft, they had everything there, except the thing that caused it. That had disappeared, as if by magic.
Mayday, mayday.
British Airways Flight 38. A 10.5-hour journey from Beijing to London. Captain Peter Burkhill has made this trip many times before.
I was operating that route a lot. It was one of my favourite flights because it was daylight. You could see the views the whole way along the route.
Burkhill and First Officer John Coward both have thousands of hours flying the 777 under their belts.
It's a joy to fly. She handles really well. She's got modern equipment. The computers are easy to use. She's got the range, the ability to do short haul as efficiently as long haul.
For these two, as for many pilots, a day on the job consists of sitting in the cockpit for long hours as computers fly the plane. Powered by two massive Rolls-Royce engines, the Boeing 777 is one of the safest planes in the industry. Nick Harris is flying back to London after a business trip to China.
The good thing was it seemed to be that we were coming in early into Heathrow. I was looking forward to getting home to the family.
Flight 38's destination is Heathrow Airport, one of the busiest international airports in the world. Nestled in the southwest corner of London, it's bordered by the A30 motorway. People who live in the nearby neighbourhood of Hounslow are well accustomed to the sound of jets taking off and landing. The area's tightly packed houses come into distant view for British Airways Flight 38. The autopilot is in control as the crew lines up with runway 27 left. As it nears the ground, the plane is buffeted by some high winds.
Just a little turbulence.
It's the first wrinkle in an otherwise smooth journey.
That's not me, that's the auto throttles doing their thing.
We were picking up wind gusts of about 20 to 30 knots, and we were fully aware that the auto throttles would be able to cope with that, so they'd be moving up and down quite a lot.
You might want to keep the autopilot on a little longer than usual, to let the wind calm down.
Will do.
In turbulent weather, the autopilot can make faster adjustments to keep a plane level than the pilots. 1,200 feet above ground.
I'll have to turn that off for now, sir.
Sure.
Thank you.
2 minutes before landing, Coward takes over flying the plane.
You have control?
Just as the two pilots had planned.
I have control.
I had a few seconds to spare before clearance to landing, and I was just tidying up my map charts.
Speedbird 38, prepare to land 27 left.
Cleared to land 27 left, Speedbird 38.
I remember looking out to see if our gate was available.
500 feet. 500 feet.
Stable?
Well, sort of.
Suddenly, there's a problem.
Pete, I can't get power on the engines. It's not giving me power. What's going on?
What do you mean?
I was looking at the engine instruments and they didn't make sense to me because we were asking for full power, but the engine instruments were not giving us any power at all.
What's going on? What?
Flight 38 is crippled in the worst way imaginable.
Well, it looks like we have double engine failure.
With neither engine providing enough power, the jet won't make it to the airport. With 152 people on board, Flight 38 is falling toward London with only seconds until it hits the ground.
This can't be happening. This is one of the most modern jets in the world.
In the cabin, there's no indication that anything's gone wrong.
On approach to land, everybody seemed relaxed in the cabin. We were just looking forward to landing.
Airspeed low, airspeed low,
Airspeed low.
And now I was looking at our impact point. I could see a set of buildings around the Hatton Cross area and a petrol station. I just knew if we were hitting those, then it was certain 100% fatalities. At that point, I felt the weight of my 4 bars on my shoulder. I am the captain. If I don't do anything, then everybody will die.
This close to the ground, Burkhill doesn't have many options. He could take back control of the plane from Coward, but doesn't think that's the right move.
First decision really was to not take control. I remember looking over at John. He was still flying the plane. Well, good. He's doing a good job. He's doing what I need him to do.
Burkhill knows that even if they manage to clear Hounslow, the jet could still smash into the busy A30 motorway or the antennas at the edge of the airport.
I thought about raising the gear. That's the biggest drag on a commercial jet. But I needed the gear to crash on. We were going to impact, and that was going to take the brunt of the impact, so I had to leave the gear down.
With a crash imminent, Burkhill has only one move left. But it comes with enormous risk.
I knew I had about 15 seconds to make a huge decision. I needed to get past those buildings. It was obvious to me that I needed to raise the flaps.
Retracting the flaps will reduce drag, but also lift. The plane will fly further, but drop faster. Burkhill must determine which is more important.
I wanted to discuss it with the crew, but this was all in a matter of seconds. I remember holding that lever for a fraction of a second.
He hopes this move will help his plane avoid catastrophe.
The effect was immediate.
Now Burkhill makes the announcement every pilot dreads.
Mayday! Mayday! Speedbird! Speedbird!
It was hard, very hard. I remember the couple of impacts and the noise.
Good God!
The landing was hard. Just a huge bang. Noise, bits falling off the ceiling.
Then I also became a passenger because we were now in an uncontrolled aeroplane. We were sliding along the ground and I didn't know what we were going to hit next. And then I thought about my wife and kids and I said goodbye to them.
The lights went out.
I could hear the wreckage breaking up. And then we stopped. When we actually stopped, I was surprised that I was still there. And then I looked around the flight deck and I was more surprised to see that all 3 of us were unscarred.
Everybody stay seated with your seatbelts fastened!
And I quickly became the captain again.
The crew switches off the fuel,
APU fire switch.
hydraulic and electrical systems.
Control switches. Come. Checklist complete.
I then had to look after my survivors. I thought 20% were dead because this aircraft was broken up.
This is an emergency. Evacuate! Evacuate!
The air stewardess then took control completely. And as she opened the door, I smelt the fuel.
We should hurry.
And realized that we need to get off this aircraft.
The big danger now is fire. Having survived the landing, passengers could be killed if flames sweep through the jet.
Jump! Jump!
I left all my luggage and just got myself down the slide.
Jump!
Let's get out of here.
I went through the galley and checked the right-hand aisle, and I was surprised to see nobody there.
Despite Burkhill's fears, there are no casualties. Outside in the cool January air, the scale of the disaster is clear.
The right wheel had actually been ripped off during the impact. The engines were just sad. They were all ripped apart. The cowlings were ripped off, and the engines were half buried. It wasn't an aircraft anymore.
I now start to realize that we've been involved in a major accident. I saw the damage to the undercarriage and to the wing.
The plane narrowly missed the A-30 and the antennas at the foot of the runway.
It could have been total devastation. If the impact had been on anything other than soft mud and grass, the likelihood of a fire was immense.
Given the amount of damage, it's incredible that only 47 people were injured.
I felt quite lucky that I was still alive. It was quite a surreal feeling.
From China, British Prime Minister Gordon Brown praises Burkhill and the crew.
I think it's right to pay tribute to the calmness and professionalism of the British Airways staff, the captain, Peter Burkhill, for what he achieved in engineering a landing that protected lives.
Investigators have some early hunches about what caused the engines to fail. They also have plenty of clues, but a key piece of evidence is already missing.
Heathrow's emergency planning swung into action.
The crash of British Airways Flight 38 dominates the news. It's the most serious accident at Heathrow in 30 years.
Heathrow Airport is a very busy airport. It is the main airport in the UK, so anything that happens in Heathrow Airport immediately hits the media.
More significantly, the 777 is one of the world's most modern and reliable jets. The accident unsettles the airline industry.
The 777 is as safe as an airplane can be. It had such a superb safety record. What on earth happened? You don't like not knowing whether it might happen to the rest of your fleet.
Investigators quickly arrive on the scene. Phil Slight is the lead engineer for Britain's AAIB, the Air Accidents Investigation Branch.
When you first approach an accident site like this, the first thought you've got is, where do I start? The plane landed about 1,000 feet short of the runway. The landing gears pushed up through the wings. The nose landing gear collapsed.
Just hours after the crash, investigators interview the crew. Captain Peter Burkhill has a first-hand account of what happened.
I think I wanted to talk about it because I knew of the innocence of the whole crew.
This isn't our fault. We didn't do anything wrong.
But the engines weren't giving us any more power.
Well, it looks like we have double engine failure.
We tried to give them more power manually, but there was nothing.
Burkhill explains that something had caused both of the jet's Rolls-Royce engines to roll back at the same time, robbing the aircraft of power.
Acceleration on both.
When you hear something of a double engine failure, you start looking at what's common. What could cause both engines to fail at the same time? So our first thoughts were that it may have run out of fuel.
A fuel shortage is rare, but it has happened before. In 1983, a Boeing 767 ran out of fuel flying over central Canada. A mistake in converting between metric and imperial measurements left the plane with much less fuel than the crew thought. At 26,000 feet, they lost power to both engines. The captain was able to glide the plane to a safe landing at an abandoned airbase. In the case of Flight 38, this theory is immediately questioned.
Jet fuel has a certain odor. Anyone who has worked with an aircraft will know the distinctive smell of Jet A1 fuel. There was certainly a lot of fuel leaking from the aircraft, from the ruptures to the bottom of the engines when we arrived on site.
A check of the plane's dipsticks confirms 2 of the tanks did in fact have fuel.
So we knew that there was plenty of fuel on board this aircraft to complete the flight.
There remain several other possible explanations for such a loss of power, and investigators must tackle them all. There is great confidence that the mystery can be solved, as any and every piece of evidence investigators could ever want is readily available. They have access to the pilot, the crew, and most importantly, the entire plane.
We were quite fortunate to have the amount of data that we had on this aircraft. Because the aircraft remained intact, we were able to interrogate lots of computers and also get lots of data from the recorders. Additionally, we had data external to the aircraft, such as radar data, and also the radio transmissions as well.
Mark Ford retrieves the plane's flight data recorders, which promise to give investigators important clues. He has another resource, the QAR, or Quick Access Recorder. While the black boxes are in the rear of the plane, the QAR is a data recorder in the front, used mainly for diagnostics.
It does have an advantage over the flight recorder, though, in that it has a greater memory capacity and can record additional parameters over and above those available on the flight recorder. You can recover the data from a quick access recorder within a matter of minutes in some cases.
Speed, altitude, control settings, cockpit conversations. In all, the various recorders have preserved 1,400 different pieces of data, which should help the investigators close the case. But when they study the QAR, what they find is chilling.
The quick access recorder data stopped about 45 seconds prior to the accident itself. Initial thoughts were that there was an electrical problem, possibly that had affected not only the QAR, but possibly the engines as well.
The 777 is one of the latest advances to computer-assisted airplanes. Pilots don't directly control the plane. Instead, their inputs are sent to a computer. Those signals are then relayed to the engines, flaps, and other systems on the aircraft.
Pete, I can't get power on the engines.
A massive failure of the plane's information systems could explain why the engines stopped working. Perhaps the computers that control them froze. Farnborough is home to the AAIB. The flight data recorder has been sent here for analysis. An electrical problem would be recorded on this device. But interpreting the information will take some time. Time investigators don't have. There are hundreds of 777s landing every day. They need to find answers before whatever brought down Flight 38 strikes again. While they wait, authorities turn their attention to the fuel recovered from the ruined plane. A bad batch of fuel could have deprived the aircraft of power just when it needed it most.
Well, fuel can be contaminated in many different ways. It can be particle contamination, it can be biological contamination, and they can get into filters to restrict the flow.
We took several samples from various points within the fuel system. So not only from the fuel tank itself, but also from remnants within fuel lines and also within various fuel components.
We managed to trace the fuel back through the documentation to a shipment of Jet A1, which came from South Korea. And that was shipped across in a tanker to China and was then transported by pipeline to Beijing Airport. We compared it with over 1,200 other batches of fuel in the UK, and it came out to be very good.
Investigators next consider the possibility of a blockage in the fuel tanks. They discover some bizarre evidence. Several small pieces of tape are recovered, along with something else.
When we were in the fuel tanks, we did find a few small articles. One of them was a red scraper.
The items were likely left over from when the plane was built 7 years ago. But while they're peculiar, there's no indication that any of them played a role in bringing down the plane.
Obviously, it's not ideal to find anything within a fuel tank. We obviously looked to see whether this would have had an effect on the fuel flow to the engines. The items were so small, they would not have caused a restriction.
As the search for answers continues, a puzzling find surfaces. Less than 3 years before the Heathrow crash, another 777 suffered a serious mid-air problem. After taking off in Perth, Australia, a Malaysian passenger jet was climbing through 38,000 feet when suddenly the plane's autopilot pitched the nose up and climbed steeply. Calamity was only averted when the pilot took manual control of the jet.
They did manage to get it safely back to base. The investigators established that this was a computer problem.
British aviation authorities consider that the electronic brain of one of the world's most reliable jets might be faulty.
The Malaysian Airlines aircraft was really quite an unnerving one. The investigators sort of pulled out the files on it and started looking over it to try and get some clues.
Did we have a problem with the electronic control system, causing the engines to roll back?
If flaws are found with Flight 38's computers, it means 777s around the world could all be disasters in the making. This thought hangs heavily over the industry. When the readout of the plane's flight data recorder is conducted in Farnborough, investigators learn that the crash could have been much worse.
There was very little they could actually have done.
It looks like we have double engine failure.
There was only 30 seconds between when they were fully aware of what was going on.
Airspeed low.
And the accident was inevitable.
Records show that soon after the engines failed, the plane started falling faster than 1,800 feet a minute, a very steep descent. But lack of power was only one factor working against the crew. They had extended their flaps on descent. It helps control the plane at lower speeds by increasing lift, but the extended flaps create drag, which slows the plane down. It takes more power to keep the plane flying with a wider wing.
Airspeed low.
I needed to raise the flaps. I knew that by raising it 1 notch to flap 25 would be the right thing to do. To reduce the drag, that's what I had to do.
Now, what he did here gave them a few extra feet.
Had the flaps been left at flaps 30, the aircraft would have struck the ground just before a set of ILS antennas.
The plane then would have slammed into the antennas, sustaining even more damage and increasing the chances of serious injuries. For their efforts, Burkhill and his team are considered heroes.
Flying is about teamwork, and we had an outstanding team.
There is no doubt. Without the flight crew's actions, Flight 38's landing would have been a catastrophe.
Now, the recordings
As they continue examining data from the flight data recorders,
continue right until the moment of impact.
investigators are no closer to solving the case.
Analysis of the flight recorder didn't identify any particular fault with the aircraft electrical system that would have resulted in both engines rolling back.
They are at least able to determine why no data was found on the quick access recorder for the last 45 seconds of the flight. It's not an electrical fault as they first feared.
The 45-second delay in the QAR recording was a result of the fact that the QAR doesn't record in real time. It buffers the data and then will record approximately 45 seconds later.
With all the information from the plane's various data recorders now collected, investigators have a precise picture of what happened. The jet was on the proper course as it made its approach to land when things went horribly wrong.
At 720 feet, the right engine rolled back. 7 seconds later, the left engine rolled back. The autothrottle attempted to command greater thrust.
It's not me, that's the autothrottle.
But the engines didn't respond.
I can't get power on the engines.
While electrical and computer problems are ruled out as causes of the crash, The flight data recorders do point investigators to the likely source of the problem.
The two most significant parameters from the quick X recorder were the fuel metering valves. Both those valves indicated that they had opened to their fully open position.
The plane's computers were calling for as much fuel from the tanks as possible. The valves were fully open, but not nearly enough fuel was reaching the engines. A plane with plenty of fuel and a working computer system still crash-landed, and investigators can't determine why. They focus on the weather on the day of the accident.
It was a very cold air mass over Siberia, so we were aware of the cold conditions, but the flight was expected to be smooth and also quick.
The plane's path took them high over Russia. The outside temperature went as low as -74 degrees centigrade. It's a potentially dangerous temperature if not monitored closely.
In cold air masses, you have to be very aware of the fuel temperatures.
When fuel starts to freeze, it produces wax. As the fuel temperature drops, the wax becomes greater within the fuel itself until it comes to a point where it can no longer flow.
We have a fuel temperature gauge on the flight deck, which is monitored at all times, and I personally look at that every time I do a fuel check, which minimum is once an hour. Basically, you don't want to get it below -34 degrees centigrade.
While they were cold, the temperatures never dipped into the danger zone where the fuel could wax and clog the system. And the fuel temperature increased significantly as the jet approached London.
We were coming through 20,000 feet, and I remember seeing -20 degrees centigrade, so it had already started to warm up.
Another potential cause of the crash is ruled out. Investigators are now running out of possible explanations.
And the expectation from the media, and also from aviation experts, was that we would have the answer within days.
But there was no comment today about the ongoing investigation.
It very quickly became apparent that that would not be the case.
They had the pilots, they had the passengers, they had the aircraft, they had everything there, except the thing that caused it. That had disappeared, as if by magic.
Despite mountains of data and physical evidence at their disposal, investigators are still unable to say what caused the crash of a British Airways 777 at Heathrow Airport. They turn to a failure of the fuel delivery system as a culprit. To prove it was responsible, they need to pinpoint anything out of the ordinary about Flight 38's journey on January the 17th, 2008.
It's a daily flight operating from Beijing to Heathrow. We wanted to work out what was unique about this flight. Why this flight in particular?
If you've got a very puzzling incident, like the 777 accident at Heathrow, you're going to mine all the data you can.
Just put them over there for now.
So we approached many operators to obtain some data of previous flights so that we could then do a comparison.
Flight data is collected from companies around the world.
And we had something like 144,000 flights in all.
But it will take months of work to analyze this enormous volume of information. To study Flight 38's fuel system more closely, huge sections of it are brought to the AAIB hangar and reassembled.
It allowed us to basically just sit there and look at it and to brainstorm and come up with ideas as to what might have caused it.
McDermott and his team consider all possibilities, from design flaws to a malfunction specific to this aircraft. The examination comes up empty.
We carried out an exhaustive and very thorough inspection and testing of the fuel system, and we find nothing wrong.
Frustrated, investigators are at a dead end.
We kept going through this cycle. We kept going back over what we'd done before. Had we missed something? And every time we went back over, we kept coming back to no.
There was no trouble with the plane's computers. It had plenty of fuel. And no problems with the fuel itself. But somehow, when it was most vital...
Mayday!
the engines didn't get the fuel they needed. The AAIB detectives have run out of suspects.
There was no clear explanation. Nothing that you'd seen before.
It's not giving me panic.
In any airplane, let alone the 777, could have explained this.
Now they turn away from the clues they have to those they don't.
Phil started coming out of a mantra, which was a quote from Sherlock Holmes.
Whatever is left, however improbable, must be the cause.
Has to be.
In this case, we always kept coming back to what's there, what could have been there that's not there now. And we come back to ice.
Suspicion that the cause of the accident was ice grew stronger and stronger.
But investigators are faced with a nearly impossible task. How can they prove that ice had brought down the plane when the evidence they need would have melted by the time they arrived? 3 months after the crash, Brian McDermott flies to Seattle to work with engineers at Boeing, the company that built the 777. If ice brought down Flight 38, they need to prove how and why.
We took the pipes from the right side of the fuel system, and those pipes and those couplings were used on the test rig at Boeing.
Ice in the fuel lines has long been a concern for jets of all kinds. But decades ago, engineers found an ingenious way to deal with the ice forming in the fuel of passenger jets. The heart of the system is the fuel oil heat exchanger, or FOHE. Cold fuel runs through thin tubes, which are surrounded by the hot oil used to lubricate the engines.
The purpose of a fuel heater is to heat the fuel up to prevent icing of the delicate fuel control system.
The FOHE is designed to prevent exactly the problem investigators suspect crippled Flight 38. But it's also a potential bottleneck in the system.
During the fuel testing, we were looking to establish where we could get a restriction that would restrict the fuel flow to 6,000 pounds per hour. And the only place that we could get such a restriction occurring was on the face of the fuel oil heat exchanger.
Investigators have to prove 3 things. First, that substantial amounts of ice can accumulate inside the fuel pipes. Second, that the ice can suddenly be released. And finally, prove that it can block a device specifically designed to melt it.
We use different methods of controlling the environment around the pipes that range from dry ice to cold fuel and to hot air to simulate the environment around the pipes that the aircraft experienced during the flight.
After each fuel cooling test, investigators look inside the pipes for ice. But they can never get much ice to form, let alone block the fuel lines.
The fuel temperature was minus 30 degrees centigrade. Very little ice would stick to the inside of the fuel pipes.
Investigators know the temperature on the accident flight didn't get much colder. So how had the ice formed?
We still hadn't answered the question of where does the ice come from in the first place? And indeed, was it ice? Or was there something else that we've missed?
Surprisingly, when the fuel temperatures are warmer, the breakthrough arrives.
If you have water in the fuel, then that water will freeze and form ice crystals. And then when the temperature gets to about minus 20 degrees centigrade, then those ice crystals will start to stick together and will also stick to the inside of the pipes.
Below minus 20, any ice crystals in the fuel are too cold to attach to the pipes. But in the sticky range, between minus 20 and minus 8 centigrade, slushy ice forms and sticks to the sides of the fuel pipes.
So when we demonstrated that ice could actually build up and grow onto the walls of the fuel pipes, there was a certain amount of surprise as to how much could actually grow.
Oh, now we're getting somewhere.
Well, the question for us at this stage was, how could that ice come off the pipes?
Investigators think they have the smoking gun. But they still can't prove how a small bit of ice could bring down a $200 million plane. They continue analyzing thousands of comparative flights to see what made Flight 38 unique. But after 7 months, they still can't crack the case.
From 35,000 Rolls-Royce powered flights, it was less than 1% that had the same features as the accident flight.
Then, on November the 26th, 2008, more than 10 months after the crash, the importance of finding an answer is underscored when the elusive culprit strikes again. Another 777 runs into trouble 39,000 feet above the United States, when one of its engines simply stops working.
Fortunately, in that case, the engine recovered and the aircraft landed safely at Atlanta.
Even though it didn't result in an accident, it reinforces concerns that there's a potentially dangerous flaw on every 777 around the world. The incident captures the attention of the British Airways crash investigators.
The Delta Shanghai flight really was investigated with huge interest. The engines were Rolls-Royce engines of the same type. So they immediately went looking for evidence of the same problem.
And in fact, they do find important similarities between the Delta airliner and British Airways Flight 38.
The aircraft had operated a long sector from Shanghai in China to Atlanta. The fuel temperatures were within the sticky range that we had defined during the research. We were able to see that the reaction of the engine was very similar to that of the 777 at Heathrow.
Later examination of the Delta flight shows no evidence of any electronic, mechanical, or fuel system problems, strongly suggesting that the culprit was indeed ice.
When we heard about the Delta flight, we were more convinced than ever that we were on the right track.
McDermott and the investigators at Boeing in Seattle continue their testing. It's been a year since the accident, and the problem hasn't been found or fixed. They've run hundreds of simulations and spent millions of dollars. They still can't get the ice in the fuel lines to clog the fuel oil heat exchanger and cause the kind of blockage that brought down Flight 38.
We came to a stage where we had not actually come up with what had caused this accident. At this time, the media and also the general public, there was a bit of unrest as to why we had not yet come up with an answer.
Industry pressure to resolve this case is intensifying. Investigators still need to know what made Flight 38 different from thousands of others that had flown under similar conditions. To find out, they retrace every moment of Flight 38's journey. The voyage from Beijing involved a gradual climb, a steady cruise, and a gradual descent. The fuel temperatures fell and rose accordingly, causing ice to accumulate in the fuel lines. That ice posed no danger unless it was released. Now investigators study the fuel flow and find that it was kept steady for most of the flight. The autopilot maintained constant speed and low power for hours, never demanding an abrupt increase in engine power until just before they reached the runway.
The approach into Heathrow was quite a turbulent approach, and the engines were demanding various levels of thrust power.
It's not me, that's the auto throttles doing that thing.
And there were 4 changes in fuel flow, one of which was a very high fuel flow of around about 12 to 13,000 pounds per hour demanded.
A closer review of the American Delta flight reveals that its engine rolled back under the same circumstances, a sudden demand for power after a long period of consistent speed. Investigators are now set to duplicate these precise conditions. They hope that by reproducing the moments just before landing, which was the only part of the flight where the crew suddenly required more power, they may finally get the answer they're looking for.
The problem that we were looking at is very, very difficult to replicate. And during what was one of the last tests, we actually managed to get all the elements together.
After simulating running engines at constant speed, investigators increased the power.
We allowed the ice to accumulate for 3 hours. and then the flow rate was increased.
What happens next breaks the case wide open. In Boeing's Seattle lab, investigators' sudden demand for more engine power causes the fuel pressure downstream of the fuel oil heat exchanger to drop dramatically. And when investigators examine this vital component,
we then saw that ice had formed across the face of it.
soft ice that had formed deep inside the fuel lines broke free when the pressure was abruptly increased. It restricted the flow of fuel to the engines. Investigators have finally found the Achilles heel hidden deep inside the 777. The tubes that bring the fuel through the FOHE jut out just above the container of hot oil. It's just a few millimeters, but was enough to prevent the ice from coming in contact with the hot surface below and melting.
Now, the ice doesn't totally restrict the fuel flowing through it. It has some porosity, so the fuel will continue to flow through. But the flow rate is much lower than it should be.
In all of the tests, only one gave investigators the result they were looking for, the one that exactly matched the journey of Flight 38. While the plane flew over Russia, water in the fuel turned to ice. At -20, it began to build up along the inside of the pipes. The steady speed of the aircraft ensured this accumulation was never interrupted. Then, as the plane approached Heathrow, turbulence resulted in the first demand for power since much earlier in the flight, and things cascaded into a serious problem.
Doing their thing. You might want to keep the autopilot on a little longer than usual.
The gushing fuel washed the ice through the fuel system until it built up against the face of the FOHE, with disastrous results.
Pete, I can't get power on the engines. It's not giving me power.
Facing a threat no one knew existed,
Mayday! Speedbird!
the pilots didn't have a chance to solve the problem. But why had the American Delta crew been able to clear the blockage, while the British Airways flight ended in near catastrophe? It's discovered that after just a few seconds of reducing engine power to idle, the blockage in the FOHE clears. But this maneuver was not available to the British Airways pilots because they were so close to the ground. Soon after the Seattle tests, Rolls-Royce redesigned the fuel oil heat exchanger.
So what Rolls-Royce did was to actually remove those protruding tubes, so you now have a flush face.
And they found that if they flattened this surface, even if ice crystals did form in the fuel, they'd go straight down the holes in the block. Very, very easy fix.
Other aircraft manufacturers are ordered to ensure that their systems aren't vulnerable to the same problem. Peter Burkhill, John Coward, and the rest of the crew of Flight 38 received the British Airways Safety Medal for their performance during the accident. It's the company's highest honor.
Crew have been presented with an unprecedented failure, and they did the best they could in the time that they had available.
The crew did as good a job as they could, and since they really only had about 30 seconds to think about what they were going to do about this, they couldn't have done any better than they did.
The ice that brought down one of the world's most sophisticated airplanes was gone by the time investigators showed up.
Weird thing about this investigation was that the culprit had fled the scene.
The inquiry into what happened consumed thousands of hours of manpower and cost millions of dollars.
These people really pulled out the stops to find out. And the reason? We have to know.
With unrelenting diligence and a little inspiration from Sherlock Holmes, the mystery was finally solved.
Whatever is left, however improbable, must be the cause.
February the 12th, 2009. Just outside Buffalo, New York.
Gear down. Folks alive.
Gears down.
Jesus Christ!
The airplane entered an aerodynamic stall. It did not recover.
It was one of the grisliest, nastiest scenes that I think I've seen.
The crash of Continental Connection Flight 3407 would be one of the NTSB's most important in decades, and would see a grieving father fight for changes to the laws governing small airlines.
I'm focused and determined to change what exists and not have another dad sitting here.
Mayday, Mayday.
Continental Connection Flight 3407, operated by Colgan Air, is en route from Newark, New Jersey to Buffalo, New York. It's been a busy flight for Captain Marvin Renslow. He's providing guidance to a new first officer, Rebecca Shaw, a former flight instructor from Seattle. Shaw's only been with the airline for just over a year. She must decide if she now wants to become a captain.
I don't know what I want to do with the upgrade. It depends where I'm based.
Well, think of it this way. If you stayed on the queue, obviously you're not making the captain rate.
Right.
But you may have a better quality of life with regards to buying a house, having a schedule.
Shaw trained to be a first officer on the plane they're flying now. A Canadian-made Bombardier Q400. It's a twin-engine turboprop, popular with regional airlines. The 45 passengers have had a long night. Their plane was held up for 2 hours at Newark, a delay considerably longer than their journey. Flight 3407 is heading northwest over upstate New York. The trip is only 53 minutes. Visibility is poor, and there's a forecast of snow and moderate winds in Buffalo.
Just some water, please.
Elise Kausner is a student at Florida Coastal School of Law in Jacksonville. She's on her way to visit her family in Buffalo.
She had 5 nieces and nephews at the time, and they had a love luncheon at the kids' school, a couple of the nephews, and they both wanted Aunt Ellie to be their guest. Any excuse to come home, she came home. She talked to all of us from Newark.
Hey.
And she called us from the lounge.
Yeah, it's been over 2 hours.
She was PO'd because of the delay.
Folks from the flight deck, your first officer speaking. It looks like at this time we're about 10, maybe 15 minutes outside of Buffalo. Weather in Buffalo is pretty foggy. Snowing a little bit there. I'd like to make sure everyone remains in their seats so the flight attendants can prepare the cabin for arrival. Thank you.
Colgan 3407, descend and
maintain 2,300.
Okay, down to 2,300. Colgan 3407.
Let's do a descent checklist, please. We can do the approach checklist along with it.
Sure. Bug set.
Set.
GPWS landing flaps selected 15 degrees.
The pilots go through a list of settings for the plane to continue its landing approach.
We're off. Yep.
Passengers can already glimpse the lights of Buffalo's suburbs. Clarence Center is on the approach path for aircraft landing at Buffalo's airport.
gear down. Lokes alive.
Gears down.
All right, flaps 15.
Extending the flaps provides more lift, allowing the plane to slow to its final approach speed.
Jesus Christ!
Suddenly, the control column starts to shake. The Q400 is slipping out of control. Captain Renslow struggles to keep his plane flying. But it seems to have a mind of its own. The plane crashes into a house at 6038 Long Street. At air traffic control in Buffalo, Flight 3407 disappears from radar.
Check Colgan there, see if he's on you.
What's his call sign?
Colgan 3407.
Nope, I don't have him.
You see anything out there?
Nothing.
All right, call the fire department.
I'll never forget the dispatcher's words, plane crash, house on fire. I immediately got my shoes on and my coat on, got in my truck and started heading down the driveway.
Firefighters don't have far to go. 6038 Long Street, home of the Valinsky family, is less than a block from the Clarence Center station.
As I turned towards the village, the whole village was aglow. You could see the smoke, you could see the flame.
Karen Valinsky and her daughter make it out of their house alive, but her husband Douglas is killed.
My initial reaction was there was no way that somebody made it out. But the EMS division reported that they had 2 people and they were taking them to the hospital. And I said, well, which firefighters are they? And they said, they're not firefighters, Chief, they're survivors from the house. I actually physically had to go to the ambulance and look inside for myself to believe.
Firefighters have never seen a blaze like this.
If you've ever gone to a bonfire and stood 5 feet from it and you couldn't take it anymore, that's what it felt like from 100 feet away.
The height of it was just unbelievable, obviously because of the fuel that was probably added to it, and the debris area was very large. It was a very, very horrific sight.
We live in the town where the plane went down, right down the road. My son was driving home from a soccer game and went right by the plane crash and called me up and said, there's a plane down in Clarence. Never really entered our brain that it was Ellie's plane.
Flight 3407 has crashed 8 kilometers short of Buffalo Airport. All 49 passengers and crew are dead, including Captain Marvin Renslow and First Officer Rebecca Shaw. But many more people could easily have been killed.
You picture a house, and to see a plane on top of this house, no more house left, no more plane, only the tail section. You're asking yourself, how in God's creation did this happen? And not wipe the whole block out.
The next call was again from my son and said, in fact, it was Ellie's plane. And they said, Dad, there's no survivors. At which point my wife shrieked and just hit the ground. Chris said he had never heard his mother make a sound like that, and I hope he never does again. So that's when we knew that she was gone, and that was probably within 45 minutes of the accident.
The scene in the morning is one of utter devastation.
Clint Crookshanks from the NTSB, and I start poking around.
Clint Crookshanks is one of the first investigators on the case.
When we arrived on scene, there was a fire still burning. It turns out it was from a gas line that had been broken in the house. The firemen would put the fire out and it would reignite every couple of minutes. It was one of the grisliest, nastiest scenes that I think I've seen.
Flight 3407 may have been a small plane, but it's the worst crash in the US in more than 7 years. It will become one of the NTSB's most important investigations. The fire at the crash site of Flight 3407 continues to burn, preventing investigators from examining the wreckage.
That's where I think the box.
The airplane had crashed into a house, and then it had burned all night long, so all the debris was basically in the house.
Our concern is that we're losing evidence. It's perishable, and if we can't get in there and get the fire out, then we're not able to maybe get a hold of evidence that might help us during the investigation.
Clint Crookshanks urgently needs to recover the black box flight recorders, which could contain valuable clues about the accident.
We knew that the recorders were in the tail part of the airplane.
Ordinarily, investigators don't go near a crash site that's still burning. But if the black boxes can't be rescued, they may never find out what brought down Flight 3407.
We started looking around and poking around into the wreckage and actually found out where they were.
Okay, whoa, it's probably in here, okay? The access panel's on the other side, so we're gonna have to cut a hole right there, okay?
The fire department produced a chop saw. We were able to cut a hole in the side of the fuselage and go in and grab the recorders and pull them out.
All right, that should do it.
To the immense relief of all, the recorders are undamaged.
Once we took the recorders out of the airplane, we put them on the jet and they were flown back to Washington, D.C. to our headquarters.
Now investigators are faced with a new hurdle. What little is left of the aircraft is hopelessly jumbled together with human remains and debris from the house.
It all burned and settled into the basement, so we had probably 10 feet of debris that we had to dig through in order to recover all of the airplane.
Authorities wonder how they can salvage any useful evidence from this chaos. They get invaluable assistance from an unusual source. A group of students learning to process crime scenes is enlisted to separate human remains from the rest of the debris.
They were graduate students from a local college, forensic anthropology students, and this was good experience for them to come dig through wreckage like this and look for human remains.
It's landing gear over there, please.
It's dirty, painstaking work, but it frees up investigators to concentrate on the aircraft ruins.
So we were on our hands and knees with brooms, with little shovels, scooping out debris, identifying it as to house debris or airplane debris, and then putting it in different piles. The first question for me as a structures engineer is to figure out if the whole airplane made it to the scene of the crash.
The wreckage is carefully studied to determine if the plane's four corners, nose, tail, and both wingtips are present.
If we find all four corners of the airplane, then we know that there was no in-flight breakup. There was nothing that departed the airplane during the flight that may have caused the accident.
One wing has been consumed by fire. The other is shattered into pieces.
Hey, have a look at this.
But investigators are gradually finding what they've been searching for.
Oh yeah, it's the last piece. It's the left one.
It wasn't until several days into the investigation, as we were scraping away some of the debris, that we actually found evidence of the left wing and the nose.
Investigators now have all the pieces they need to conclude that the entire plane is at the crash site. Whatever caused the disaster was not the result of a breakup in flight. The tragedy of Flight 3407 is under intense scrutiny at the NTSB offices in Washington. Officials there try to determine if some kind of malfunction caused the crash.
On this particular accident, we knew it was a landing accident, so we wanted to check the aircraft's performance, and then also we checked for flight control continuity.
Much of this responsibility falls to Scott Warren.
My role in the investigation was to be the systems group chairman for the safety board, so I was in charge of looking at all of the aircraft systems.
Warren analyzes the aircraft's cockpit voice recorder, or CVR, to determine if there were any indications of a problem in the cockpit.
Attendants can prepare the cabin for arrival. Thank you. Is that ice on the windshield?
He discovers that 6 minutes before the crash, the crew of Flight 3407 had noticed a buildup of ice on the aircraft.
Got it on my side. You don't have yours?
Oh, yeah. Oh, it's lots of ice.
Ice can be a deadly threat to any airplane.
If an aircraft has ice on it, it will have more drag on it, so it'll require more power to maintain a given airspeed.
Oh yeah, it's the most I've seen on the leading edges in a long time.
Until a year ago, Rebecca Shaw had no experience with ice on an aircraft.
I'd never seen icing conditions. Never de-iced. Never experienced any of that.
When ice accretes on a wing, it adds weight to the airplane, but most importantly, it changes the shape of the wing. And of course, it's the shape, the curved shape of the wing that actually creates the lift. So by changing the lift characteristics of the airplane, it makes it less able to fly.
You know, I'd have freaked out. Like, I'd have seen this much ice and thought, oh my gosh, we were gonna crash.
Observing that there was ice on the airplane was an important thing to do. But then it would be important to turn around and verify that your anti-ice and de-ice equipment was on, and there was no indication on the voice recorder that they actually rechecked.
Flaps 15.
The CVR reveals that only minutes after the crew detected ice, a device called the stick shaker went off. It was a warning that the plane was about to stall, literally to fall out of the sky. Shortly afterwards, the aircraft did precisely that.
We know there were icing conditions. The only question was, were they bad enough to induce this airplane to have a failure?
Ice is now the chief suspect in the crash of Flight 3407.
If it's ice, let's prove it.
We were all convinced that we had an icing accident. We said, yeah, it's going to be an icing accident. We just got to make sure we look for these few key aspects of icing, verify that, and we're good.
But some of the victims' family members are less convinced.
Our initial thought was that it was an ice-related incident, that it was an icy night and brought the plane down. And as we began to talk to people who knew airline travel, who were pilots themselves, they would look kind of askance and say, I don't think so. That doesn't make sense.
Some investigators share that suspicion. Scott Warren knows a plane like the Q400 has a sophisticated de-icing system. It's designed to keep ice from building up on the wings and other critical parts of the aircraft. To prevent ice accumulating, the plane has rubber bladders along the front of the wings, called de-icing boots. A series of valves uses air from the engines to inflate the boots and crack the ice off the wing.
Those boots are designed to inflate periodically, and that inflation breaks off the ice that's accumulated on those leading edges.
Warren now wonders if the crew of Flight 3407 actually turned on their de-icing equipment. He studies data from the plane's other black box, its Flight Data Recorder, or FDR. It tracks the workings of crucial aircraft systems, including the de-icing mechanism.
We know from the FDR data that the de-icing system had been selected on by the crew, and it was on during the majority of the flight, and certainly at the end of the flight it was recorded in the on position.
But now Warren needs to figure out if the device was actually working.
Just because the data records that the system is on, that's a start, but you can't necessarily believe that one piece of information.
The only way to know is to find what remains of the plane's de-icing system and determine if it was active when the aircraft went down. Clint Cruikshank's team hunts for a crucial component of the system, the valves.
Excuse me. Okay, everyone, I just want to...
For the de-ice valves, we said, here's what it looks like. Look for something like this. If we can find those valves and we can test them and see if they're operating correctly.
The valves were very important to us because they are the key component that moves air from the engines where the bleed air originates for the de-icing system.
Okay, good. 5 more to go.
Five of the plane's 6 de-icing valves are eventually recovered.
Some were badly burned, some were in fairly good shape. And we took those valves and we conducted as much testing on those valves as we thought was appropriate for the level of damage. We looked at the level of electrical conductivity, and we looked at the pressure testing. We looked at a wide variety of things depending on the condition of the valve itself. And as far as we could tell, all those valves were working properly.
Is that ice on the windshield?
Got it on my side.
Now investigators have to consider the possibility
Oh, yeah. Oh, it's lots of ice.
that there was so much ice on the wings that the de-icing system couldn't get rid of it fast enough.
Oh, yeah. That's the most I've seen on the leading edges in a long time.
It has happened before. In Roselawn, Indiana, a French-built commuter plane crashed in 1994 after suffering a catastrophic buildup of ice on the wing. By analyzing how much power was needed for the plane to maintain its airspeed, investigators reach a surprising conclusion.
Basically, the aircraft was flying as if it had a relatively small amount of ice on it, but a very manageable amount of ice.
Looks normal.
It was not overloaded, it was not excessive.
If ice didn't bring down the plane, something else must have caused it to stall. Warren studies the Q400's operating manual to learn the plane's stall speed, the velocity at which it can no longer generate enough lift to stay in the air. He discovers that in the conditions Flight 3407 was flying through, it's roughly 111 knots. He now compares the plane's stall speed with its actual airspeed just before the stall warning went off. 131 knots, well above the danger zone.
Flaps 15.
When the stick shaker went off,
Jesus Christ!
they were not necessarily at the edge of a stall. They were still 20 knots or so away from the stall.
This new revelation deepens the mystery of Flight 3407. If it wasn't stalling, why did it fall out of the sky? Investigators turn their attention to the critical seconds before Flight 3407 went out of control. They look for clues that could explain why the stall warning went off when the aircraft was flying well within its safety margins. They discover that this plane has a unique feature known as a reference speed switch. It governs the sensitivity of the plane's stall warning.
Very few airplanes, in my experience, have such a switch. This airplane is the only one I know of that has an actual switch on the overhead panel. It was designed by the manufacturer to be an extra safety feature.
Some kind of variable ref speed?
Pilots are supposed to turn on the reference speed switch when they're going to be flying through icing conditions.
And we'll probably be picking up some ice.
When in the increase position, it reminds pilots to fly faster to counteract any drag effect ice will have on the aircraft.
When you are in icing conditions and ice does accrue on the wing, it can cause the stall speed to go up And so this ref speed switch correspondingly causes the warning to come on sooner or at a higher speed.
What that switch does is it basically changes the trigger settings for the stick shakers.
So we had to ask the manufacturer, how does this switch work? And what we found was it was part of the system's description that the crews got when they went through training, but they didn't get a lot of training on how to handle that switch. It seemed like it was too simple to worry about.
Investigators need to know if the crew of Flight 3407 had turned on the reference speed switch, triggering the stick shaker at a faster than normal speed. The flight data recorder doesn't show whether the switch was on. Investigators must find another way of determining its position at the time of the accident.
Clint here.
Clint Cruikshanks is given a new priority.
All right, I'll see if we have it.
Recover the ice protection panel from the Q400's cockpit, where the reference speed switch is housed. Since the panel was in the cockpit, finding it is a challenge.
Most of the front end of the airplane was consumed by fire, and so we didn't find anything except for little balls of molten aluminum, little wire bundles, and a lot of ash.
But after an extensive search, Cruikshanks discovers that the ice protection panel is one of the few pieces of the cockpit that survived.
Bingo.
However, the knobs and switches are barely recognizable. Cruikshanks examines the charred panel to check the position of the reference speed switch. It was set to activate stall warnings at higher than normal speeds.
We did find the ref speed switch in the wreckage, and it was in the increased position.
This discovery only raises more questions.
We'll probably be picking up some ice.
The cockpit voice recorder indicates that as Renslow was beginning his descent into Buffalo, he commanded his plane to fly at the normal approach speed.
Gear down.
But what's strange is that with his reference speed switch on, he actually should have been flying faster, as this is what the switch would remind him to do. So why wasn't he? The plane's computer warned the crew to fly faster, according to the settings they had configured, by displaying a set of red bars on the airspeed indicator.
You may have a better quality of life with regards to...
These bars are meant to warn the pilots that a stick shaker activation is imminent.
Whenever it's right.
If you're looking at the airspeed indicator, you should be aware that you're getting slow, and the stall warning may come on.
Jesus Christ!
It seems Renslow and Shaw were caught off guard. Still, they could have easily corrected the situation.
Once the stick shaker had activated, they could have turned the switch off, or they could have put the nose down and increased their airspeed.
It's clear to investigators that Flight 3407 wasn't in danger of stalling when the stick shaker went off. So now they need to know exactly what happened after the stall warning was activated. An animated simulation of the crash is constructed, based on information from the flight recorders.
Watch what happens just after the stick shaker goes off.
It illustrates that just after the stick shaker was triggered, the plane suddenly pulled up. This action dramatically slowed the aircraft, and at this point it did stall.
Essentially, the airplane entered an aerodynamic stall from which it did not recover. It pitched over and hit the ground.
Investigators are dumbfounded. Flight 3407 wasn't stalling when the stick shaker went off, but a few seconds later it was. The crew's every action during that brief time now demands careful scrutiny.
What did they do?
It's a puzzle. How could a trained flight crew take a plane that wasn't stalling and in the space of a few moments make it fall from the sky?
Anytime you have an apparent stall for no apparent reason, that's a mystery. You would expect that no flight crew would stall an airliner. So the question is why?
The focus of the investigation now switches from the plane to the crew, specifically on the moves they made during the critical seconds after the stall warning sounded.
We wanted to see if the way they flew the airplane was the way they were trained, according to the standard operating procedures that are portrayed in their flight manuals.
The flight data recorder retains information from more than 1,000 different aspects of the Q400's flight operations. From the airspeed and altitude to the position of the rudder pedals and throttles. It also records the movements of the most critical flight control, the control column. Pilots use the control column to change the position of the elevators and ailerons, which manage the direction of the plane. The flight data recorder stores information not just about the control column's position, but how much force is applied to it as well.
The FDR records what the control positions were. It has sensors built into the control column, it has sensors built into the control wheel.
What Scott Warren finds when analyzing the control column's position is stunning. In response to the stick shaker, Captain Renslow should have pushed the column forward to bring the nose down and gain speed. But for some reason, he did the exact opposite.
We found that the crew, instead of pushing forward, which is the normal response to a stick shaker triggering, the crew was actually pulling back on the controls.
This had the effect of pulling the nose up, causing the airspeed to drop and tipping the aircraft into an actual stall. Captain Renslow had apparently mishandled one of the most elemental piloting maneuvers: how to recover from a stall. Above everything, it requires gaining airspeed to get out of the red.
The recovery procedure is fairly simple and straightforward. It requires pushing forward on the controls and adding full power. At any point in time, had the captain pushed forward on those flight controls, he had a reasonably good chance of recovering quickly.
From everything we've gained, that stall was recoverable on a repeated number of levels on a repeated basis. There was no reason for that plane to go down.
Investigators also learned that First Officer Shaw, in trying to help Renslow deal with the crisis, inadvertently made things worse.
I put the flaps up!
She retracted the flaps, reducing the amount of lift as the plane struggled to stay in the air.
Had the first officer simply called out, "You're stalled," advanced the power, pushed the nose over, the airplane would have been able to recover.
From a human point of view, it's sad to recognize that those sorts of things happened and the tragedy that came from that.
It's concluded that Captain Renslow's failure to properly respond to the stall warning was the primary cause of the crash of Flight 3407. As the issue is now pilot error rather than mechanical failure, human performance investigator Evan Byrne is brought on board. His first question: why hadn't either Renslow or Shaw noticed that their airspeed was too low for the icy conditions?
In this case, we can look back towards the fact that there were clear and conspicuous cues of the deteriorating airspeed that were not heeded by the captain.
Byrne listens to the cockpit voice recording to try to understand what might have led to that oversight.
Where you could be home with your husband to take care of and all that stuff.
He learns that the crew had been talking throughout the flight. The conversation continued during the landing approach. It's a violation of a rule known as the sterile cockpit, which bans non-essential conversation during critical phases of the flight.
You're gonna be upgraded in 6 months. Blah, blah, blah.
Quite simply, it prohibits conversations that aren't related to the operation of the flight.
Let's do a descent checklist, please. We can do the approach checklist along with it.
Bug set.
Byrne also discovers that because of the cockpit banter, the crew performed critical checklists and briefings late.
Off. Hydraulic pressure and quantity.
Distracted, the crew probably didn't see the red bar indicating they were flying too slowly for the conditions the plane had been configured for.
On. Approach checklist complete.
Rock and roll.
When crews deviate from standard operating procedures and perform checklists late or don't make the required callouts, they become more vulnerable to subtle mistakes that they may make inadvertently that could lead to startle and surprise or unanticipated events that they have to respond to.
The evidence is unequivocal. The crew of Flight 3407 was badly distracted throughout the approach.
Came in when we interviewed, and he said, "Yeah, you're gonna be upgraded in 6 months."
They had forgotten a key setting they had made that required them to fly faster than normal. They had missed indications that they were flying too slow for icing conditions. Then Captain Renslow had reacted incorrectly to a stall warning, sealing the fate of the plane. Evan Byrne wonders, what could have caused a trained airline flight crew to have made such missteps? He finds a clue on the cockpit voice recording.
Excuse me.
The crew was showing signs of fatigue. Could Renslow and Shaw have been too tired to function effectively on the flight deck? It's a tough question. Answering it will require tracking their movements during the 72 hours leading up to the crash.
It's basic gumshoe detective work in the investigation where we're trying to collect as many facts as we can.
Byrne interviews the families of the pilots.
Could I speak to Mrs. Renslow, please?
He studies the pilots' mobile phone bills and records of text messages. He searches the airline's computer system to determine if and when the crew used it to check their schedules. He needs to track their every move.
And what time did Rebecca leave the house?
We're talking to colleagues or other pilots, check airmen, instructors, and we ask all those people about the pilots, about their recent activities.
He learns that neither pilot actually lived anywhere near Newark, but could not afford to stay in hotels on their salaries. Captain Renslow was earning $60,000 annually at Colgan Air. First Officer Shaw was being paid less than $16,000 a year, substantially less than an average bus driver. As a result, both pilots had made long cross-country commutes to Newark. Captain Renslow from his home in Florida, and Rebecca Shaw from Seattle, Washington. In fact, Shaw had commuted all night from Seattle on a cargo flight that connected through Memphis. Captain Renslow had spent the night in the airline's crew lounge at Newark Airport, after having already worked 2 days. He was seen sleeping on a couch in the lounge. It was against company rules, but pilots who couldn't afford housing near the airport did it anyway. Records show that at 3:10 a.m. on the morning of the crash, Renslow was awake. He checked his work schedule on the airline's computer network.
Next stop, Buffalo.
At 7:29 a.m., Rebecca Shaw sent a text message to her husband, telling him she'd arrived safely in Newark.
Hi, honey, it's me.
Phone records indicate that later in the morning, Captain Renslow was on the phone several times. Rebecca Shaw was noticed having a nap, catching up on the rest she'd lost flying in the night before.
It's not a lot of sleep.
We ultimately concluded that it was likely that both crew members were experiencing some effects of fatigue at the time of the accident.
Her job is to watch the airspeed. Her job was to watch the instrument panel, and my view is she was fatigued to the point where it's like right here in your soul dull. I think that's where she was, and he just was not capable. He was just, he shouldn't have been flying an airplane.
The revelation leads John Kausner to become a fierce advocate for changes to the industry. He raises awareness among both lawmakers and the public about the need to improve regulations governing pilots at regional airlines.
This is just saying we support 3407 families, their fight for aviation safety, and these representatives and congressmen and senators have done that for us, and we're very appreciative.
He takes his fight all the way to Washington, D.C.
We needed to do something, and so we began to advocate in Washington weekly, every other week. I mean, we've made innumerable trips down there. And immediately the families just gelled. We all attended the hearings and began to say, this is what we can do.
The crash of Flight 3407 focused the world's attention on a growing safety problem. The relatives of those who were killed will help eliminate that threat. The crash of Flight 3407 exposed wide-ranging shortcomings in the regulations that govern regional airlines. These smaller airlines now make up half of all daily passenger flights in the US. Their pilots are generally younger, less experienced, earn less, and work long hours.
Their levels of safety are way different from the majors. They have a much lower threshold in training, in ability, so in pay, obviously, so they can't attract a higher qualified pilot.
There are pretty low wages, pretty difficult working conditions, and we don't seem to attract the same level of applicant that we used to. Some regional airlines get into a bind, and they have to hire the first people that meet the minimums.
In the US, of the 7 fatal accidents involving passenger jets over the past 10 years, 5 have involved regional airlines. Those include the crash of Delta Connection Flight 5191 in August 2006, which killed 49 people when the crew took off from the wrong runway. John Kausner's campaign to change laws governing pilots has paid off.
We relied on your support. We needed your support. You nurtured us. We want to thank all of you from all of us.
A year and a half after the crash, under pressure from Kausner and other victims' family members, the US Senate passed a bill which toughens training requirements and forces the FAA to draw up new rules on pilot fatigue. Studies into the problem of overtired pilots are already underway. At the University of Iowa, researchers are developing a system that could help pilots resist fatigue, stay engaged with the critical task of flying, and prevent future tragedies like that of Flight 3407. Thomas Schnell is a human factors engineer.
We use a number of neurocognitive and physiological sensors that we apply on subjects, pilots that we invite for our studies.
Is going to be free-floating. We'll just go ahead.
He's studying how pilots stay alert on the flight deck as a test subject conducts a cross-country journey in a simulator. Using sensors, he can determine how alert and engaged a pilot really is. The research could lead to the development of fatigue detectors on airplanes.
We are trying to predict pilot state so that we can adjust something on the flight deck to prevent the problem from getting worse or starting in the first place. We monitor brain activity, eye movement activity, heart, the EKG and respiration and other parameters in an effort to figure out what the pilot's or the crew's state is. Are they fatigued, overworked? Are they disengaged or distracted? This section is where they were really drowsy, and you can see that the gaze has become kind of bored.
Schnell instructs the flight simulator to trigger a major systems failure in the cockpit.
It's no good. Everything's dead. Hydraulic systems have failed. Flaps are not deployable.
Crank up that heat map so we can see what this brain activity was.
Brace for impact.
When a crew is fatigued, what you might see is their reaction to events may slow down. So you'll see mistakes being made on the flight deck.
It's precisely these kinds of mistakes on the part of Renslow and Shaw that ultimately crashed Flight 3407 and killed 50 people.
It's a tragedy that should not have happened, that was foreseeable, was preventable, and it's repeatable if we don't do something about it. I'm focused and determined to change what exists and not have another dad sitting here.
gentlemen, we're beginning our descent towards Amsterdam Schiphol
You'll have to
Airport.
turn that off, Vanessa. Thank you.
Turkish Airlines Flight 1951 is preparing to land in Amsterdam.
Amsterdam, Turkish 1951, descending to 7,000, speed 250.
The crew is flying a state-of-the-art Boeing 737.
Flaps 15.
Localizer alive, localizer capture.
In the final moments of the flight, the landing turns into a catastrophe. The plane falls like a rock. The crash of Turkish Airlines Flight 1951 involves the most popular plane on Earth. With nearly 1.5 million passengers boarding 737s every day, investigators need to figure out if the problem was with the plane or with the pilots flying it.
Mayday, Mayday.
On the morning of February the 25th, 2009, Turkish Airlines Flight 1951 becomes the first plane to crash at Amsterdam's Schiphol Airport in more than 10 years.
It smashed into the ground really hard. It made a tremendous noise.
The plane hits the ground in a muddy field just north of runway 18 right. Since the crash was so close to the airport, rescue workers arrive quickly. Most of the passengers have survived, but many are badly injured. Survivors are taken straight to local hospitals. Images of the Amsterdam accident quickly spread around the world. This is the third crash of a passenger jet in the past 6 weeks. The sudden nature of this accident adds to the mystery. It doesn't take long for the Dutch safety board to arrive at the scene. They will be investigating this accident, but they won't be alone. The crash involved an American-made plane, so the U.S. National Transportation Safety Board sends Joe Sador, one of its most experienced investigators, to Amsterdam.
When it's a non-U.S. registered aircraft that crashes overseas, such as this Turkish Airlines, we are the state of manufacture and design of the airframe, and also, in this case, the engines.
Fuselage in 3 large pieces, engines forward of the main wreck site.
Flight 1951 was one of the most advanced aircraft in the skies, the Boeing 737-800 series. It's designed to travel longer routes at higher altitudes.
The new generation 737 is still the best airplane Boeing ever built. We developed an airplane that had an improved wing, improved avionics, simpler systems that required less maintenance.
Investigators know this isn't just any plane. The 737 is the world's best-selling commercial jet. Finding out why this one crashed is imperative. There are more than 5,000 of them in the skies. They carry about 1.5 million passengers a day. Investigators must quickly determine if there's a flaw with the plane that could cause another accident. What they know so far is that Flight 1951 had been traveling from Istanbul, Turkey, to Amsterdam. There were 128 passengers on board the early morning flight, including 4 engineers from Boeing.
Ladies and gentlemen, we're beginning our descent towards Amsterdam Schiphol Airport. Please raise your seat backs to the upright position and stow away your tray tables.
There was no mention on board of any kind of trouble in the cockpit. The crash has killed 9 people, including 3 members of the Boeing team and the pilots in the cockpit.
See if you can get me some aerials of the crash site.
There are eerie similarities to another recent accident involving a Boeing aircraft. British Airways Flight 38.
Approximately a year before this, there had been a 777 short landing at Heathrow, which had a dual-engine flameout.
In that accident, a Boeing 777 fell to the ground short of the runway. The British Airways pilots reported that both their engines stopped delivering power just before landing. At the time of the Turkish Airways crash, the cause of that accident hasn't been found. Like in that case, investigators have plenty of clues to work with. The plane and its engines are largely intact. The flight data recorder and cockpit voice recorder are found in good condition. There are also plenty of survivors to describe what happened. According to the passengers, the landing had been routine, but then suddenly the plane simply dropped out of the sky and hit the ground. But perhaps the biggest clue comes from the crash site itself. The wreckage is not spread out. It tells investigators that the plane could not have been traveling forward at high speed when it hit the ground.
The way the aircraft had crashed, it did appear to be some sort of a landing accident in which there was moderate control of some sort.
The pattern of debris and the passenger reports point investigators to an immediate suspect: the engines.
The engines issue was a very big issue in my thought process at the time, initially.
There's no evidence of fire on the fuselage. In many crashes, fuel in the plane's tanks ignites on impact. The lack of fire raises an obvious question. Did the engines stop running because Flight 1951 had simply run out of gas?
That was one of the first thoughts that I had was, did this airplane have fuel aboard? Because otherwise, how does a 737 literally fall out of the sky on approach to an airport?
But the location and condition of the plane's engines suggest that perhaps they didn't quit in flight.
Sure looks like it was running.
When we first looked at where the engines ended up, the initial impression was that they probably were producing thrust at impact, given that they were so far forward of the main wreckage. That was just a very general conclusion.
Only the flight data recorder can tell investigators how much power the engines were generating in the seconds before the crash.
Lots of fuel. Rules that out.
It doesn't take long to discover that there was plenty of fuel in the plane's tanks. Flight 1951 definitely did not run out of gas. Passengers report that in the final seconds before the crash, the plane hit what felt like turbulence. It points investigators to a well-known culprit, a microburst. A microburst is a powerful column of air that shoots out of storm clouds. It can literally slam a low-flying plane to the ground.
If an airplane flies into that at approach speeds, you're not going to be flying anymore. You're going to come out of the sky. Certainly, it was one of the things that all of us took a look at the beginning. Was there a microburst?
In 1985, a Delta Airlines flight was caught in a microburst while landing at Dallas-Fort Worth Airport. The plane hit the ground short of the runway. 137 people were killed. Investigators learned that there were heavy clouds above the airport at the time of the accident. A powerful gust of wind may well have accompanied them. The flight data recorder will have recorded wind speeds outside the plane. Investigators will need to analyze the flight data to prove the microburst theory. In the meantime, the rescue has led to an unusual discovery.
There was 3 pilots in the cockpit, which is unusual. This is a 2-crew cockpit. So why was that 3rd pilot there?
Since none of the 3 pilots survived the accident, it's all the more urgent for investigators to retrieve the data from the cockpit voice recorder. It records conversations in the cockpit. They're in luck.
Because of the way that the aircraft crashed, access to the recorders and the condition of the recorders was excellent.
The reason for the 3rd pilot is soon uncovered.
Flying standard arrival route. Visibility 3,500 meters, expected to decrease to 2,500 meters.
For First Officer Murat Sezer, this had been a training flight of sorts. He was new to the airline and was being shown the intricacies of landing at Amsterdam's airport.
In the Jepson charts, which is what all pilots use to navigate to and from Schiphol, there's 102 pages of information on Schiphol alone. So there's dozens of approaches.
Runway 18 right has 3 high-speed exits to the left.
The captain, Hassan Arisan, was doing double duty. He was training his first officer
Make small corrections as we get close to the runway.
and was in command of Flight 1951. It's because Captain Arisan was teaching that there was the third pilot in the cockpit. Olgay Ozgur was a safety pilot. He was there to keep an eye on the flight's progress during this training mission.
The purpose of that second set of eyes is to make sure that the captain and the first officer, if they're in a situation where it's a little bit of a training portion of the flight, that they don't miss something.
We got a clean recording?
The voice recorder reveals that the 3 crew members began preparations for landing when still above 8,500 feet.
Amsterdam, Turkish 1951, descending to 7,000, speed 250.
But the voice recorder has picked up an unusual sound, a warning that makes no sense at this stage of the flight.
One of the investigators from Boeing was a engineering pilot that came and helped with the CVR. And he's listening to see when, or are there any unusual sounds that can be heard that would not be normal.
Speed okay for ILS 18 right. Descend to 4,000, ILS 18 right.
The alarm keeps sounding. It's the landing gear configuration warning horn. Captain Arisan continually dismisses it.
Turkish 1951, descend to 4,000, ILS 18 right. Landing gear.
Is that the landing gear warning? They're at 8,300 feet here.
The warning is a solid clue, but investigators can't yet see how it could possibly have caused a crash. The crew of Turkish Airlines Flight 1951 got warnings to extend their landing gear while still thousands of feet in the air.
On the initial listen, we heard a gear warning horn occur as the aircraft was approaching, when it was still up and it was coming in about 10,000 feet and below.
Investigators now turn to the flight data recorder to help solve some of the mystery surrounding this flight. The analysis of wind speeds outside the aircraft is completed. It's clear, none are drastic enough to have brought down the plane.
Evidence of a microburst.
But the flight data recorder does provide some valuable insight into the cause of the landing gear warning. One of the instruments that measures altitude had the plane already on the ground.
When we looked and saw the radio altimeter data, on the recorder it showed about 8,000 feet, and then immediately it went down to about -8. -8 feet is an indication that the aircraft's on the ground, but of course it's still at 2,000 feet.
The Boeing 737 is equipped with 2 separate altimeters. One measures air pressure to determine the plane's height above sea level. That reading is displayed prominently in the cockpit on both pilots' flight display.
10, set, sir.
The plane is also equipped with a radio altimeter. It's made up of 4 antennas. 2 transmit signals to the ground, and 2 others read the signal that bounces back to determine the plane's height.
It's precise. It's very, very precise. Pressure altimeters can sometimes be not as accurate, and radar altimeters are 100% accurate if they're working properly.
One antenna feeds the reading to the first officer's display. The other feeds the captain's instruments. In the case of Flight 1951, the captain's side was wrong most of the flight. Investigators go back over the CVR and make a puzzling discovery.
Amsterdam, Turkish 1951, descending to 7,000, speed 250. Radio altimeter.
Captain Arisan seems to have known that the landing gear warning was being caused by a faulty radio altimeter.
The airplane thought that it was low to the ground and the gear was not down. And the captain recognized that the problem was really in the radio altimeter, showing him that they should be on the ground, and he goes, it's just the radio altimeter.
Throughout much of the approach, the captain's radio altimeter had been displaying a reading of -8 feet, triggering the warning to lower the gear.
They treated it like it was a nuisance.
Turkish 1951.
Descend to 2000.
2000, 1951.
Investigators dig for any other abnormalities. They learn that with Flight 1951 still about 17 kilometers from the airport, controllers directed the pilots to begin their final turn to line up with the runway.
Turkish 1951, left heading
210, cleared approach.
18 right.
Left 210, cleared ILS, Turkish 1951.
210 set, sir.
This turn puts Flight 1951 in line with runway 18 right. It's equipped with an instrument landing system, which sends out a signal outlining the ideal descent path to the foot of the runway. The autopilot follows that glide path until the plane is a few hundred feet from the ground. Then the pilot takes over. It makes landing almost effortless.
The ILS is pretty easy to follow. It's a video game. My daughter has flown in a simulator and can land a 737 using the ILS.
The crew begins configuring their plane for landing, unfazed by the warning horn that's repeatedly triggered by the malfunctioning radio altimeter.
Flaps 15.
10 kilometers out, Flight 1951 picks up the ILS signal that will guide the plane to the runway.
Localizer alive. Localizer capture.
The safety pilot, Olgay Ojgur, now reminds Captain Arasan about the failed altimeter.
We have radio altimeter failure, sir.
Okay.
Turkish 1951.
Runway 18 right. Clear to land.
Clear to land, thank you.
Investigators are stumped. The crew knew about the malfunction and continued their approach. How had it then caused them to crash? Clearly, there was more to this accident than a faulty altimeter.
The whole premise of airline safety, the way we build the airplanes, the way we fly them, is based on the idea that we can have any number of failures and we should still be able to arrive safely. The radio altimeter is just one instrument. There's no way in the world that that one instrument, if it fails, should be a major cause of worry that we're going to have a crash.
Investigators wonder if the crew had been given proper guidance for their approach. They turn to exchanges between the pilots and the controller who guided them in. They carefully review every instruction.
Turkish 1951, descend to 4000. Speed okay for ILS 18 right. Turkish 1951, descend to 2000. Turkish 1951, left heading 210, cleared approach 18 right.
By following the controller's instructions, the crew made their final turn much too close to the runway.
So to intercept properly, they should be here.
International guidelines call for approaching planes to intercept the signal that guides them to the runway from below. It's so pilots don't have to make any drastic last-minute course corrections to get to it.
To intercept here, they had to descend.
But Flight 1951 was given instructions that brought it to the threshold of the glide slope while still way above it. It's a common practice at Schiphol because it gets planes to the runway faster.
Because they were so close, they had to capture the glide slope from above. Although it is an unusual situation, it is one that can be handled by a flight crew if it is managed properly.
Approaching a glide slope from above is more difficult, mostly because the crew has to suddenly slow the plane and descend rapidly to intercept the signal.
We also call this a slam dunk approach, and some pilots like it, some pilots don't. It's a little bit harder, and things happen quicker when you're above the glide path trying to intercept from above, and it's just a challenge for a lot of pilots.
The approach from above increased the crew's workload, but it's standard practice at Schiphol Airport.
I've flown into Schiphol dozens of times, and I expect it.
If the controller's instructions had somehow overtaxed this crew, their conversations would indicate it. They're just 5 kilometers from the runway.
1,000.
Check.
Flaps 40. Speed brake.
Speed brake armed. Green light.
One thing at a time. Landing gear.
Gear down. 3 green.
Flaps.
Flaps 40. Green light.
500.
All lights on.
Please warn the cabin crew.
Cabin crew, take your seats.
Then, real trouble. A stall warning.
Speed, sir.
I have control.
100 knots of speed.
Arisan fought to save his plane, but just 400 feet above the ground and only 1.5 kilometers from the runway, the Boeing 737 suddenly fell straight down. It only took a few seconds for it to hit the ground.
Turkish 1951.
The recording sheds light on the final minutes of the flight. The crew was configuring their plane for landing well after it should have been done.
Flaps.
Flaps 40. Green light.
Most airlines have regulations that call for a flight to be stabilized, to have all checklists completed by the time the plane hits 1,000 feet.
In instrument conditions, you're required at 1,000 feet to have basically everything done. The airplane is configured, you have slowed, you have run your before landing check, and you have received your landing clearance. And from 1,000 feet on in, you just monitor the instruments, and we're looking for the runway.
Please warn the cabin crew.
Cabin crew.
In fact, this crew was still running their checklist up to the moment the crisis hit, 460 feet above the ground.
This approach was not stabilized.
Because the aircraft was unstable, the flight crew was in a very high workload environment in the last 1,000 feet of flight.
The radio altimeter was malfunctioning. The aircraft was giving off warnings. The crew was assigned a challenging approach, and they were executing a checklist late. But none of this explains why Flight 1951 crashed.
In these type of accidents, you can never get inside the head of the pilots. And that's a very frustrating type of accident.
But the flight data recorder does provide another intriguing clue. Moments before Flight 1951 hit the ground, the plane's engines were at idle, hardly providing any power. Perhaps this accident is a repeat of the Heathrow incident.
The engines, it was interesting to note, were at idle approximately the last 2 minutes of the flight, until the very end when the thrust was increased again. That was a big red flag right there. The question is why was that the case?
But then they spot something that's very different from the accident at Heathrow.
Retard flare mode.
For some reason, while still more than 1,000 feet above the ground, the plane's computer began preparing to touch down. In retard flare mode, engine power is reduced to idle by the flight computer, and the plane's nose automatically pitches up to the flare position. Planes should only be in this configuration just before they touch the ground.
The autopilot raises the nose to break the descent. The auto throttles brings the power back to flight idle, and you touch down with the power either all the way in idle or just about to be in idle.
But Flight 1951 went into a slow, nose-up position well before touchdown, causing the plane to fly slower and slower throughout its descent. So why was Flight 1951 in landing mode? And why hadn't any of the 3 crew members noticed how slowly they were flying?
So, what else was going on when the engines went to idle?
The trouble seems to start with the malfunctioning altimeter.
We had to look at the system as a whole and to see how that -8 affected the other systems on the aircraft. And that was a very big portion of this investigation. We had to say, how did the autopilot use that data? More importantly, how did the auto throttle use that data?
The computer that flies the plane consists of two main systems, the autopilot and the autothrottle. The autothrottle determines how much power to ask the engines for, while the autopilot controls the plane's altitude and direction. The two systems work independently of each other, and only one of the radio altimeters provides information to the autothrottle.
In this case, I had to learn everything there was about radio altimeters and autothrottle systems, which I didn't know before.
The pieces of the puzzle begin coming together when they find the connection between the faulty radio altimeter and engine power.
The radio altimeter provides information to the autothrottle from the captain's side.
The only altimeter feeding information to the autothrottle was the captain's, and it was wrong. It showed -8 feet throughout most of Flight 1951's approach. It's beginning to look like the faulty radio altimeter triggered the events that led to the crash. Investigators need to know what went wrong with it. On a 737, the transmitting and receiving antennas for both radio altimeters are lined up underneath the cockpit. 3 of the antennas were all but destroyed in the crash. They can't be tested. But one antenna from the captain's side is undamaged. Investigators consider 2 possibilities: a failure of one of the components, or some sort of interference that caused the faulty reading. The only component that survived the crash checks out. The computers that control the system also work. But investigators do make a curious discovery about them. They aren't the same ones that were installed on the plane when it was delivered to Turkish Airlines 7 years ago. This find changes the focus of the investigation.
The maintenance aspect of this accident aircraft was one that we looked at as deeply as we could.
When the plane's maintenance log is studied, investigators find that the radio altimeter on this plane had a problematic history.
We got additional data from Turkish Airlines, and that data showed that on this one aircraft, of the past, I believe, over 1,000 flights, there was about 150 flights that had faulty radio altimeter systems.
The documents show that a little more than a year before the crash, both computers were replaced because of complaints they were causing faulty readings. One of the incidents involved a radio altimeter reading of -8 feet.
So that was telling us that there was an issue that had been there. The issue did not just occur on this flight.
The faulty readings persisted. Mechanics repeatedly swapped the computers and replaced the antennas to try to solve the problem. It's determined that Turkish Airlines tried several ways to fix the altimeter, but they couldn't find a repair that worked. At the time of the accident, Turkish Airlines had a fleet of 52 Boeing 737-800 series airplanes.
It's on page 93.
When we reviewed the maintenance data, we found that radio altimeter problems had been written up several times on both the accident airplane and the fleet.
Investigators discover that in the year before the crash, Turkish Airlines dealt with 235 system faults with the radio altimeters on their 737s. Fixes ranged from replacing and exchanging antennas, cleaning of the systems, exchanging and replacing the computers, and installing gaskets to shield the system from possible water damage.
It's not like they weren't doing anything about it.
The Turkish Airlines maintenance personnel knew that the radio altimeter problem was one of their highest issues with regard to maintenance.
16 of those altimeter repairs were made to the plane that crashed in February 2009. If the problem was so widespread, investigators wonder why it hadn't caused serious problems before this accident. They don't have to dig too far back to find out that in fact it had, on this very same plane.
On 2 recent flights, they had the exact same problem.
Twice in the 48 hours leading up to the accident, the radio altimeter showed a negative reading, putting the plane into retard flare mode. Both times the crew noticed the problem, disengaged the auto throttles, and brought the plane in for a safe landing.
You just disconnect it and fly the airplane.
In the months after the crash, other operators come forward with similar stories. In Australia, in the Netherlands, in Canada, in Austria, pilots report their 737s going into retard flare mode when the left radio altimeter showed a faulty reading. Each of those crews reacted the same way. They disengaged the auto throttle and pushed the power back up manually. They all landed safely.
Things are going to break on an airplane, and usually you're able to identify that and take that out of, make it so that it's not a threat for the landing.
In 2008, Boeing received a whopping 2,569 reports of faulty radio altimeters on their latest 737s. But very few of those cases involved the plane going into retard flare mode.
Hardly any reports at all.
Boeing also tried but couldn't find the cause of the failures. They concluded that the radio altimeter problem was not a threat to safety because the 737 gives off enough warnings so that crews can intervene and land safely. In fact, in every instance where the radio altimeter failed, crews were able to recover. Turkish Airlines Flight 1951 seems to be the one exception. Investigators still don't know why.
It really got us wondering of what happened. And that's when we started to look really closely at the actions of the flight crews while it was on that final approach in less than 1,000 feet.
Finally, as investigators again revisit the last minutes of Flight 1951, the circumstances of the tragedy become clear. They see a remarkable sequence of events that transpire to bring down this plane.
So, what was happening when the plane went into retard flare mode?
They discover that the plane went into landing mode and pulled back power at the worst possible moment, exactly as the crew was descending to meet the glide slope.
It masked what was actually happening.
As the crew configured their plane to drop down to meet the glide slope, they expected the plane to slow down as part of that maneuver. But the plane was actually slowing down because the computer was in landing mode. That's why none of the 3 pilots said anything about the throttles moving to idle.
It was insidious. Where it first captured in the retard mode, it didn't hurt them at all because they were actually high and they were a little bit fast. And the pilots actually wanted the power back anyway. In fact, the throttles may have already been in the flight idle mode as they were trying to get down and slow down.
Right, the trouble starts here at 8,300 feet, 13 miles out from the airport, minutes before the crash.
Amsterdam. Turkish 1951, descending 7,000, speed 250.
Turkish 1951, descend to 4,000. Speed okay for ILS 1B. Right.
Radio altimeter.
Would the crew have known that because of that radio altimeter they would have gone to a retard flare mode in the throttles? No.
It was a common problem at the airline, but the crew couldn't see the risk it posed this flight.
We have an airplane that was malfunctioning in a very minor way, but in a way that, if not caught, could and did metastasize into something much more virulent.
Turkish 1951, descend to 2,000.
2,000. 1951.
Turkish 1951, left heading 210, cleared approach 18 right.
Left 210, clear ILS, Turkish 1951.
Now left at 210 degrees, maintaining 2,000 feet, brings the flight in right here, 5.5 miles out. They now have to intercept the glide slope from above.
At 2,000 feet, with the glide slope below them, the pilots have to reduce their speed while descending steeply.
Speed 140.
They believe the throttles are moving back for the descent to the glide slope. In fact, the auto throttle is slowing the plane down because it's gone into landing mode. It will continue to slow the plane until it stalls.
What we found is that when the flight crew was doing their before landing checklist, each one of them was doing something while they should have been monitoring their airspeed.
For the next 100 seconds, no one notices what's happening until it's too late.
Established altitude set.
1,000.
Check.
Flaps 40.
Speed set.
The experienced pilot recognized that the first officer was probably a little bit behind on the approach, so he calls for flaps 40 and moves the lever, informing the first officer that he has done so. He's trying to help the first officer catch up to the position of the aircraft.
Speed brake.
Speed brake armed. Green light.
One thing at a time. Landing gear.
The plane is now 700 feet from the ground.
Gear down. 3 green.
Flaps.
Flaps 40. Green light.
In their haste to complete their checklist, none of the 3 crew members notice the warnings that their speed is dropping dangerously. First, a red bar appeared on their flight display. Then, when the airspeed continued to drop, a flashing box appeared around their actual airspeed to draw the pilot's attention to it. At this point, no one sees either.
Cabin report confirmed.
The aircraft is now 600 feet from landing.
When things start changing colors, it's a warning to you, it's a caution to you that you're approaching the limits of the aircraft.
Missed approach. Altitude set.
500.
So all of these indications the crew has in front of them saying that the aircraft is slowing down. During that time, they were still completing their checklist.
Of course, the aircraft is getting closer to the ground.
In fact, it's less than 500 feet from touchdown.
And right before the stick shaker started, the captain told the safety pilot,
Please warn the cabin crew.
Cabin crew, take your seats.
Speed, sir.
I have control.
By the time they advanced the throttles to full power, it was unrecoverable. They were too low for the engines to catch up.
And that's it. It's now too late to save this plane. They all knew about the altimeter problem, but knowing didn't help.
Boeing also didn't foresee the potentially deadly effect of a faulty altimeter. But on February the 25th, 2009, it triggered an unusual sequence of events that brought down a jetliner and killed 9 people. The official report into the accident blames it on a convergence of circumstances.
There is never, ever just one cause to an airline accident. It simply doesn't exist. Maybe someday God will swap one out of the sky, but until then, there's never one cause.
The Dutch report also points out that Boeing could have realized the problem with the radio altimeter system could have had an impact on safety. Given that no one foresaw how that failure might cause a crash, the Turkish Airlines accident raises a big question. Are airplanes becoming too complex? Investigators have determined that Turkish Airlines Flight 1951 crashed mainly because the pilots didn't recognize the consequences of the warnings they were getting.
Turkish 1951, descend to 4,000.
This is not the first plane to crash because the crew didn't understand what their plane was telling them.
Turkish.
Our problem is not the automation. Our problem is the depth of the training and the ability of the human beings to recover from mistakes made in interfacing with the automation.
Mika Ensley studies the relationship between pilots and technology.
We haven't really designed the automation to take best advantage of what people do well and take away the parts that people don't do well.
In 1996, The crew of an Aero Peru 757 crashed when the pilots couldn't decipher contradictory warnings about their altitude and airspeed. The plane flew into the Pacific Ocean. 61 passengers and 9 crew members were killed. In 1995, the flight management system on a Boeing 757 could and should have steered the plane to a safe landing in Cali, Colombia. But a last-minute change to the flight plan meant the crew had to reprogram their computer. They mistakenly entered a course that took them headlong into a 9,000-foot mountain. 159 people died in the crash.
The cautionary tale here is that we can get this equipment, we can get these silicon-based units, if you will, so sophisticated that we can't talk to them effectively. And when they go berserk, or they have a problem, or we misprogram them, we end up putting ourselves and our passengers in danger while we're trying to figure it out.
NASA is working on something called the Integrated Intelligent Flight Deck. It's a project aimed at helping humans better use the technology that surrounds them in the cockpit.
They're looking at automated flight manual systems, voice recognition systems. They've developed new kinds of microphones that are bone-conducting chips. They're developing new displays for understanding the ground environment, for being able to detect where other aircraft are in the environment.
What some researchers are finding is that the best technology shouldn't replace pilots, but work with them.
Really integrating people with technology more effectively has to do with designing the displays so that you can really understand what it's doing, and you can make it simpler to understand how to make it do what it is you want it to do. You shouldn't have to push 16 buttons through 8 levels of menus to figure out what's going on with the system. It should be integrated and presented effectively. It should be as easy to communicate with as the person next to you.
Boeing and Airbus, the 2 largest manufacturers of passenger planes, take very different approaches to the relationship between humans and technology. Airbus gives the flight computer much of the decision-making power in the cockpit.
In their view, this is a way to prevent a lot of human errors by making sure the airplane doesn't do something that's going to cause a crash, even if the humans want it to.
But Boeing has a different view. Its philosophy is to provide information to pilots and have them make decisions.
Having more information is better for the pilot than having the pilot in the loop, in the equation, so to speak. I kind of like that.
Airbus will argue vociferously and in continuous fashion that that view is archaic and incorrect. I think the jury is still out.
The final report into the Turkish Airlines tragedy blames the crash of Flight 1951 partly on a failure of technology.
The erroneous radio altimeter data caused the autothrottle to go to an improper mode that is, of course, not a good situation.
The cause of the radio altimeter failure was never uncovered. The Dutch investigation asks Boeing to improve the reliability of the system.
We learned a lot about the radio altimeter system and how it affects the autothrottle system. Boeing is currently working on system improvements to prevent this type of autothrottle event from occurring again.
But the report also faults the crew for not noticing that their airspeed was dropping dangerously low, in spite of the fact that there were 3 pilots on board.
Forget that you got an autothrottle. You look at the airspeed, and you look at the altitude. You look out the damn window if you want to, but airspeed is a crucial component of staying alive in an airplane. And you always need to know what your airspeed is.
But to Mika Ensley, the crew's failure to monitor instruments is entirely understandable and may be more the fault of the instruments than the crew.
It's actually very difficult for people to be monitors of automation. One of the things that people don't do a good job of actually is monitoring. We're very good on-the-spot decision makers. We're very good at coming up with creative solutions to problems, but repetitive monitoring is the kind of thing that actually people aren't very good at all. So what we have to do is design automation to work with people in a way that keeps them more actively, cognitively involved and in the loop, and not just monitoring a piece of automation to say, is it doing what it's supposed to be doing?
Who's the ultimate computer? The pilot, the individual who should be able to say, I don't know what this thing is doing to me, but I'm punching it off and flying the airplane. Fly the jet. Probably the smartest thing we ever learned to say in our training in the airlines, fly the jet. Do that first or nothing else counts. That's what they forgot to do.